All right, guys, this is April 30th, and we're starting section 6.1. If you can believe it, we only have this chapter and one more before we're done. So let's see how we're doing. So we're going to be looking at linear systems and two variables with applications. So you guys have solved systems with two equations and two unknowns before. Let's just recap how we do some of that. So first example, they just want to verify that this is a solution. So if that's the case, when I put 150 in for A, and they're using A and C for variables, and I put 350 in for C, it needs to work for both of them. So we're just gonna double check. Is 150 plus 350 500? Yes, okay. Is 9 times 150 plus 5 times 350 3100? Yes. So if that's the case for both of them, it's a solution. If either one of them isn't true, it's not a solution. Okay, solve the system by graphing. And so you got to do a couple of things here, guys. One, you need to make sure that you solve for y so that you can put it into the y equals. Okay, so the second one, y equals 3x minus 5, is already there for you. This one, you're going to have to subtract x, divide by 2, and put that into your y equals. Graph it. Now, looking at the graph, it clearly looks like 2, 1 is a solution. You can certainly double check that back here. 2 plus 2 is 4, and if I put a 2 in there, 6 minus 5 is 1. That certainly works. Otherwise, on your calculator, if you go to second calculate, intersect is one of the features in there, and it'll tell you the point that it intersects at. So there's another option for you guys. If you can solve both the equations for y, put them in your calculator, see where they cross. Okay. In general, substitution, if you follow the examples in the book here, it looks like it kind of showed up weird on my screen. But if you look at page 508 in the book, it takes you through, solve one of the equations for x in terms of the other one. Just look at page 508 in your book for this one. Somehow PowerPoint is not agreeing with me these last couple days, but we'll take you through an example of it to show you how it works. You'll probably remember anyway. Okay, so solve using substitutions. You've got a set of equations here. 6x plus y equals 1 and y equals 2x minus 3. Step 1 is to solve for one of the variables. And it turns out y is already isolated. Y equals 2x minus 3. So then I'm going to take that expression, that 2x minus 3, and I'm going to put it back in for y in the first equation. So then that gives me 6x plus, instead of y, 2x minus 3, equals 1, and then I've got just a little bit of algebra to do, right? 6x and 2x is 8x minus 3. Add your 3, divide by 8, x equals 1/2, so that's one part of the solution. Now, once x equals 1/2, I can put that back in for this x here in the second equation. 2 times 1/2 minus 3 is negative 2. 1/2 negative 2 is my solution then. Okay, so that's how substitution works. Operations that produce equivalent systems, and we're going to use this when we do elimination here, but you can change the order of the equations. It doesn't have to come first one, then second one. You can switch them. Replace the equation with a non-zero constant multiple of the equation. So I can multiply any row by whatever I want, okay? And I can replace the equation with the sum of two equations. So I could add or subtract the two equations and replace it with what I get, okay? And we're going to do that here with elimination. So, the first thing that I want to do, you notice here I've got x in the first column, y in the second column, and here y then x. So I'm going to align the columns first. Okay? So I'm going to write 2x minus 3y equals 7, and then I'm going to switch these two around and write 5x plus 6y equals 4. Okay? Then, if you look at these two equations over here, 2x and 5x aren't the same, 3y and 6y aren't the same. But if I multiply this first row by 2, then I'll get a 6y and a 6y, and the y's will match up. So I'm going to do that. I'm going to multiply the first row by 2 and get 4x minus 6y equals 14. And I'm going to leave the second row the same, 5x plus 6y equals 4. And now if you look at those columns, the y values are the same. And so I can either add or subtract the equations. I choose to add because that will eliminate the y's. So if I add these two equations together, 4x and 5x is 9x. Negative 6y and 6y is nothing. 14 and 4 is 18. Now all I have to do is divide by 2 to get x equals 2. And then I got to put that back into an equation, and it really doesn't matter. I chose to put it back into the first one 2 times 2 minus 3y equals 7. If you were to solve there, that's 4. Subtract 4, you get 3. Divided by negative 3 is negative 1. So in the end, 2, negative 1 is your solution for that using elimination. So we wanted to align the x's and y's in the same column. We had to, in this case, multiply one of the rows by a number so that it would work. And then the rest of it, I think you guys have done before. Okay, so this is the process for elimination, right? Write each equation in standard form, ax plus by equals c. That's aligning those columns. Multiply one or both equations by a constant that will create coefficients x or y that are additive inverses. So one's 5 or negative 5, or that kind of thing. Combine the two equations using vertical addition and solve for the variable that remains. We did that. Substitute the value from step 3 into either of the original equations to get the other unknown, and then write the answer as an ordered pair. Okay, so let's do this one more time. Okay, I've got x, y constant, so it's kind of in standard form here. But, here I have 5 halves x and 3x, I have 3y and 4y, they're not the same. I chose to multiply the first row by 4, giving me 12 here for y. The second row by 3, giving me 12 for y as well. Okay, so when I multiply this by 4, I get 10x minus 12y equals 4. Okay, multiply this row by 3, I get 9x minus 12y equals 18. Okay, now when I look at this, the y's are the same, and so if I subtract those two equations, since they both have the same sign, I'm going to eliminate my y's. So 10x minus 9x is just x. Negative 12y minus negative 12y is nothing. 4 minus 18 is negative 14. So now I've got x. I then need to plug that back into one of the equations. I choose to plug it in here because I don't want to deal with the fraction. So 3 times negative 14 minus 4y equals 6. If you solve this, so you get negative 42, you add 42, you get 48, divided by negative 4 is negative 12. There's my solution, okay? So sometimes you have to multiply both rows by something to get the x's or y's to be equivalent, okay? One more time here. First one's in standard form, the second one isn't, so I gotta get the y over on the left side. So I chose to add the 8y. I put aligned columns, but that's what I'm doing. So 3x plus 4y equals 12. And then the second one, I'm going to add the 8y, so 6x plus 8y equals 24. Okay, 3x and 6x, not the same. 4y and 8y, not the same. I choose to multiply the first row by 2. That will give me 6x and 6x. Okay, so didn't change, or I'm going to change the first row. 6x plus 8y equals 24. Second row I didn't change, but hey, look, they're exactly the same, you guys. So when I subtract these two columns, I get 0 equals 0. Now, when your variables subtract out like that, you've got one of two scenarios. Either you have an infinite number of solutions, which is what we have here because what's left, 0 equals 0, is true, or you have no solution if you had 0 equals 7, for instance, which is never true. And so the way we have to write this answer is we have to write a blueprint for finding the solutions. We can't just say there's an infinite number. It doesn't mean any ordered pair you put in works. I got to put in a blueprint. So what I did is I said, well, let's just let x be x. So in our solution, we're going to let x be x. And then I need to solve for y in terms of x. So if I take this equation and I solve for y, so I subtract, or back here, if you will, subtract 3x, and I have negative 3x plus 12, divide by 4, and I get negative 3/4 x plus 3. That's what I'm going to call my y coordinate, because those are equivalent. And now if I pick an x, like 4, I get 4 for the x coordinate and 0 for the y coordinate. And so that would be a solution. There's an infinite number, but they all have to follow that blueprint. So that's kind of what we're looking at there. All right, so example 7. Now we're getting into kind of a word problem version of this. We're still going to solve a system, but we have to think of how we're going to write the equation. So it says a jeweler is commissioned to create a piece of artwork that will weigh 14 ounces and consist of 75% gold. She has on hand 2 alloys that are 60%, 80% gold respectively. How much of each should she use? So we've got two unknowns here. We're going to let x be the number of ounces of 60% alloy and y be the ounces of the 80% alloy. Okay, so there's two things I know. That we have 14 ounces, so I can say that x plus y is equal to 14. And I know that I want a 75% alloy. So if I take 60% of how many ever ounces of the first one I have, plus 80% of how many ever ounces of the second one I have, I'm going to get 75% of the total number of ounces, which is 14. Okay? So again, they're both in standard form. I've got the columns aligned, but the x's and y's aren't the same. So I chose to just multiply the first row by 0.6 to get the x's to be the same. So 0.6x plus 0.6y equals, if you take 0.6 times 14, you get 8.4. The second equation I left alone, except I multiplied the 0.75 times 14 to get 10.5. Now when I look at these two equations, if I subtract them, I lose the x's, or I eliminate them. So I'm going to do that. 0.6 minus 0.8 is negative 0.2. 8.4 minus 10.5 is negative 2.1. Divide out, and I get 10.5 ounces of the 80% solution. Well, I know they're supposed to add up to 14, so if I take 14 minus 10.5, there must be 3.5 ounces of the 60% solution. So I think the hardest part here is setting up your equation. Solving it is no different than what we did on the previous slides. Okay, so I think you're good with that. Let's look at one more word problem here. An airplane flying due south from St. Louis, Missouri to Baton Rouge, Louisiana uses a strong, steady tailwind to complete the trip in only 2.5 hours, meaning the wind was pushing the plane and speeding it up. We can add the speed of the wind to the speed of the plane. On the return trip, the same wind slows the flight, and it takes 3 hours to get back. Well, now you're going against the wind and it's pushing you, so you're subtracting that rate. Okay? If the flight distance between the cities is 912 miles, so their distance is going to be the same in both trips, what is the cruising speed of the airplane and how fast is the wind blowing? So I have two unknowns. The rate of this plane without any wind, and then the rate of the wind. So I got to come up with an equation. The idea is distance equals rate times time here, you guys. So if I let my unknowns be r and w for rate of the plane and rate of the wind, when I'm going with the wind, my rate is going to be the sum of those two, because the wind is going to speed you up. So that's your rate times your time, because it took 2.5 hours on the flight there, equals your distance of 912 miles. On the way back, since the wind is pushing against us, you take the rate of the plane minus the wind. So this will be your rate right here, times 3 hours, it took longer to go back, equals that same distance of 912, okay? So let's go ahead and distribute here so that we can get it in standard form. So 2.5r plus 2.5w equals 912. 3r minus 3w equals 912. And then I chose to, in order to try to get the variables to be the same, if I multiply this row by 3 and this row by 2.5, I will align those values. So I get this new equation, 7.5r plus 7.5w equals 2736. And then 7.5r minus 7.5w equals 2280. If I subtract the two, I'm going to lose my r's. I could add them and lose the w's. It doesn't really matter. But if I chose to subtract, so I'm going to lose the r's. 7.5 minus negative 7.5 is like plus. So I'm going to get 15w. When I subtract these two, I get 456. Of course, I have to divide by 15, and I get w equals 30.4. So the wind was blowing at 30.4. I don't remember if the units were kilometers per hour or miles per hour. Okay. And then I need to put that 30.4 back in for w. So I chose the first equation here, and I'm going to replace my w right here with 30.4, and then I just need to solve. Multiply these, subtract it, divide by 2.5, and I get the rate of the plane to be 334.4 miles per hour. So just remember, whether you're going with the wind, against the wind, in the water, with the current, against the current, you're going to set up your equation something like this, okay? So the next couple of examples, I'm not going to go through. If you want to look at them in the book, you certainly can. We'll get to the assignment here. So be careful, 6 through 54, multiples of 3, so 6, 9, 12, etc. Okay, and then 69, 72, and 75. A little different than how it's written on the paper. I hope you guys have noticed this by now, but good luck with that. Again, office hours from 11 to 11:30, or email me if you have questions. I'd be happy to help. All right, good luck.